Thank you very much. Thank you for that nice introduction. So I'm very excited to have the opportunity today to talk to you about deformation correction and the problem of first print yield, and specifically the areas that Velo as a company has been investing in the last several years to try to combat these two common problems in additive manufacturing. So I want to talk about three specific areas in which Velo is helping to address the problem of first print yield and geometric accuracy. The first one I'll talk about is recoater contacts. The second one is laser overlay and distortion errors. And then the final one, which I'll spend the most time on, is thermoplastic deformation during the printing process itself. Velo has put a lot of effort in the last several years in terms of how to properly simulate this type of thermoplastic deformation, with the ultimate goal of being able to do deformation correction upfront in the preprint software, such that when the part is actually printed, you get to the correct net shape at the end of the build. The first place I want to start, though, is with recoater contact, because this is one of the areas which sort of jumps out most obviously as being different about the Velo machine versus other laser powder bed fusion systems. So in terms of first print yield and the origins of yield loss on first article prints, a lot of them can come down to recoater contact on conventional systems. There are multiple things that can happen when the recoater contacts a part. The first thing that can happen is that if the part is relatively weak or at a high aspect ratio, the part will oftentimes just move out of the way and the recoater will basically plow it over, which causes geometric accuracy issues and part defects. Another possible thing that can happen is that the part is protruding out of the powder bed and will actually damage the recoater, which can then cause defects within the powder bed itself, which then on subsequent layers get lazed onto the parts themselves. An example of this is shown in the bottom right-hand corner here, a very classical powder bed streak, which then imprints itself onto the part. And then finally, the ultimate form of recoater failure is just the entire build failing because of a catastrophic collision between the recoater and the parts. To that end, many things have been developed, or many tricks have been used in the industry to date to try to minimize these types of failures. Things like using heavy usage of supports to anchor the parts firmly to the build plate to try to prevent them from ever sticking up out of the powder bed. And even things like in the bottom left-hand corner where parts have to be oriented in very specific directions relative to the recoater to prevent the recoater from plowing into them and causing a failed build. So what Velo does differently is we use a non-contact recoater to put the layer of powder down on top of the build. The way this works is that we do a dispense, shear, and level all in one motion, and this happens well above the actual build plane where the part is being printed. What happens because of this, because there's no physical contact between the recoater and the actual part, you no longer have to worry about things like part collisions, moving the parts, or any defects being generated on the recoater. This also allows us to do certain things like having parts be built entirely free-floating within the powder bed, because you no longer have to worry about physically moving the parts as you're doing the print. So this is one area in which Velo is helping to reduce first print yield failures. The second thing I want to talk about is laser overlay and distortion. This is a schematic of a multi-laser system. And this schematic would be pretty general for any multi-laser laser powder bed system, but this one specifically is for the Velo 2-laser Sapphire system with two 1 kilowatt lasers. So in this case, you've got two different lasers up in the optics box that are both impinging upon their respective galvos, and they're being directed onto the build plane. The idea is that if both lasers are told to fire at the exact same spot on the build plate, that the laser beams actually end up at the same spot of the build plane. There's always some error associated with this, though, and we would call that error the laser overlay error, which is basically how far the two beams are away from each other when nominally targeting the same spot. The second form of error that happens at this point is laser distortion, which is when you take a specific beam and you move it a pre-described position along the build plane. How far does the laser beam actually move when you move it along the build plane? So if I'm targeting 100 millimeter travel, do I actually get 100 or do I get 99 or 101? These are the two common sources of geometric errors when building parts on multi-laser systems. So the Velo system comes built in multiple different metrology and sensors that allow you to monitor different aspects of the machine health before you actually begin prints to help reduce the scrap that comes from being off on any of these areas. This is an example screen showed from the print software itself. These are just buttons that you can press when you walk up to the system. We have buttons related to checking beam stability. So this is an automatic test to see whether or not the system has any thermal lensing and whether or not any optics need to be cleaned. We've got a thermal sensor test, which determines whether or not the melt pool alignment is proper with the coincident beam. And then finally, the one I'm talking about here is the laser alignment button. So what happens when you click this button is that it actually does a pre-described routine over the entire build plate, and it measures at 500 different spots on the build plate exactly how far off the two lasers are relative to each other. And you can see an example there on the left-hand side where you're basically firing a pattern with the two different lasers and then using the sensors on the system to measure how far off they are. The average distance between the two lasers is given by the alignment offset there. In this case, it's about 8 micron error between the two lasers. And then the standard deviation of all of the errors all over the build plate is given by the laser alignment quality, in this case about 30 microns. In addition to doing the overlay test, it also allows you to do a distortion test where it's comparing where the pattern is being generated for one laser relative to itself as a function of how far away the two objects are from each other. And the standard deviation of that particular error is then given by the distortion quality. So this is something that you can check before or after any given build with an automated routine by just clicking a button on the system. And if anything is out of spec, you can always align it in real time using the same screen. To show how that works in practice, this is an example build where we basically printed different wall sections at various distances apart from each other on a build plate and tested how far apart the parts actually were printed over several runs to determine the run-to-run variability. In this case, we're targeting a dimensional accuracy spec of 0.2% plus or minus 50 microns. On the next slide, I've got the actual results that come from that particular measurement, where on the y-axis, you have the measured error in terms of the gaps between the two parts. And on the x-axis is how far apart the parts are to begin with. And what you can see is that the blue line is that 0.2% spec line, and the red line is what we're actually achieving. So even when you're using the entire build area, so have parts that are 300 millimeters apart from each other, the overall error in their placement is still less than 150 microns by using this in situ capability. The last thing I want to talk about is deformation correction. So there are many different types of deformation correction. I'm going to go through a couple different examples and what it is that the Velo software allows you to do to help mitigate these. So one common mode of deformation is when you have relatively thin objects connected to a larger mass. And it doesn't even have to be that extreme of a larger mass. This is an object which we lovingly call the bat at Velo. And it doesn't, at first glance, seem to be that challenging of a part. You've got a center lobe that's growing off in one direction and then two thin fins growing off the side of it. Well, what happens when we actually print that part, which you can see on the left-hand side here, and then we use a 3D scanner to measure the displacement of the geometry to what was intended in the CAD file, you can see that those edge fins are actually deviating from their expected position by over 1.3 millimeters in this case. So you can get very large macroscopic deformations in these types of objects as you're printing it, just due to the residual stress that's building up while you're printing the part. So to help combat this, Velo has generated its own preprint software, which we call Flow. And there are a couple of unique aspects of Flow relative to other preprint offerings on the market. The first thing, which you can see all the way on the left-hand side, is that it uses native CAD workflow, which means on a typical system where you would have a CAD file and then you would first convert it into an STL representation, on Velo software, you just directly import the CAD file into the software itself, and you do all of your surface selection in terms of putting supports and process overrides on the CAD part itself. This is very powerful in terms of being able to be more user-friendly and easier to manipulate your object, but it really plays into part in the second part, which is the simulation. Being able to import the native CAD directly allows you to have very fine control over the ability to mesh the object, which then allows you to do thermoplastic simulations and be able to predict deformation and also whether or not you're going to have build failure issues. Finally, the last step of it is prior to printing, you can then review in our composer exactly what print operations are going to be done on each layer to make sure that everything is the way intended. So I'll talk in more detail about the simulation software. So the key aspect here is that the ability to do accurate process simulations. The two big reasons for that is one, being able to predict build failures before they actually happen. So the simulation software basically allows you to know by layer what is the local stress on the object and the deformation at any given time. And so what we're looking for here is on any given layer is the vertical displacement of the part in excess of what the system is able to tolerate, such that it's going to cause an issue. The second thing you're looking for is whether or not locally you're exceeding the yield strength of any component of the part, particularly on supports, to indicate to you whether or not you're likely to have support failures in the middle of the build, which will then cause your object to move and potentially cause the part to be scrapped. The final thing is because even in the case where you don't have build failure or any supports breaking, you still have this large-scale deformation that's present in many parts. And the software is now able to actually pre-deform the geometry such that when you print it, it deforms back into the correct net shape. An example video is being shown here of exactly how that happens. So in this case, it's focusing on this very simple test structure, which is just shown to sort of give an idea as to how it works. So as printed, any sort of horizontal bar that's printed on the laser powder bed system will have a tendency after it's cut off the build plate to warp up into a smiley face structure. What this does is that it pre-simulates that deformation that's going to happen, and it distorts the geometry down such that after the part is finished printing, it's warped up now to the proper shape. What you can see here is an example of this exact part being printed on the Velo system, both using the object preprint correction on the left-hand side and then the uncorrected version on the right-hand side. And you can see in this case, the uncorrected version has the very characteristic smiley face pattern of that deformation, whereas on the corrected case, we're able to properly counter deform that. So in order to do this properly, though, there's a lot of work that had to go into being able to do accurate simulations. One of the big ones I already mentioned before is the ability of the Flow software to use native CAD import. As most of the software people within the company will say, simulations is pretty much just a meshing problem and everything else is sort of secondary. If you can get a really high quality mesh and of the right density in the right places where you need it, that is what's going to give you both accurate simulations and also reasonable timescales in order to do these simulations. So the ability to import the parts directly in native CAD gives us a lot of flexibility in terms of doing this meshing, such that we can carefully compromise between these two aspects. So I'll lay that out more explicitly on this slide here, which is showing sort of accuracy versus speed trade-offs. So it's not very helpful to be able to do these types of simulations if it takes days or weeks or months or even indefinite amounts of time to actually get the results back, because that doesn't work within a regular process flow. We need to be able to get the simulation times down into the hour range such that the engineers who's preparing the build can either react to what the simulation is telling them is going to happen during the build, or to be able to apply these counter deformations. So in order to do that, we have careful control of our meshing to simultaneously optimize for speed and accuracy. In the upper right-hand corner here is a typical part that we would print on one of our systems. In this case, it's a shrouded impeller that's about a 50 millimeter diameter. And when printing or when simulating this type of object, we're able to do it on the 18-core PC that comes with the Sapphire system for our preprint preparation on the time scale of minutes to hours, which is enough time, or it's a short enough time to allow it to be usable for the engineer to either make any adjustments that they want to in terms of how the part is being supported before it's being printed, or to apply this counter deformation. Now, in the bottom right-hand corner is an example of a part, though, that is the entire build volume, or almost the entire build volume. So this is a part that's 280 millimeters in diameter and then almost 400 millimeters in Z height. In this case, it's not feasible to do these types of simulations on a single computer in order to get the appropriate speed and accuracy. So what the software team has done at Velo is they've allowed the simulation to be done in a very highly parallelized way, which allows us to use resources like local clusters of computers or the cloud to do the simulation in parallel and then merge the results back together into the final predicted deformed shape. What this does is it allows us to take parts that are nominally the entire size of the build chamber and still complete the simulations in a matter of hours, which is a reasonable time scale. So next I wanted to go into a couple examples of what the simulations tell us about common deformation that's seen on objects. An example here is an object that we had originally printed without thinking too hard about what the scale of these deformations were going to be. On the left side there, you can see that there's this simple, central, very massive hub of material along with a series of fins that are grown off the side of it. In the middle there is what the flow simulation says in terms of what kind of displacements are going to happen. And in this case, the very large mass at the center of the part is going to cause plastic deformation all the way on the edges of those fins and cause them to move by over a millimeter in this case. On the right-hand side is what you see actually happens when you print the part. And we've got two cases, one where the blades are connected to the hub as was simulated, and then the other case where the blade was printed just by itself, so it didn't have this large mass tugging on it. And you can see in this case that the unconstrained blade relative to the one that's connected to the hub, you can see this very large difference in shape and deformation that occurred, validating the simulation. Another very common example that we found on many parts of areas to watch out for large-scale deformation is connections. So this is a toy part, but it's very indicative of things that happen on real parts. In this case, it's a simple vertical wall structure, which then turns into a series of planes growing at 45 degrees, which then merge at some point within the Z height. So it's a very simple part. When you actually run the simulations on it, though, you end up with a very complicated answer, which is that the part is going to move a lot. In this case, right at the connection point where these metals come together, they actually pulls the connection point down by about 650 microns, and at the same time bows out the edge walls by another 650 microns. And so you can see in this case that this would then give indication to the engineer, either do I want to change orientation or change the support strategy on this particular part to try to avoid these types of deformations, or they could use the Velo software to do the pre-object deformation, which would allow them then to print the part and have it come out to their correct shape. The last thing I want to focus on before ending is that there are some limitations to these types of simulation approaches that we've had to work through. One of them is that the accuracy of the simulation is highly dependent on what hardware you're using to do the print and also what exact parameter set you're using. So to show that, on the right-hand side here, I've got a very simple experiment where you're printing horizontal bars, which are supported to the build plate. And in this case, you're just changing the thickness of how thick of a bar you're printing. As you thicken the bar, it ends up displacing less because the object becomes stiffer. So you get this characteristic downward shape in terms of the deformation versus how thick the bar is. Now, if you use one of the recipes that we've developed and you run it across multiple different machines, you end up with the blue, red, and green curves here, where you get very consistent deformation as you print the same objects. But if you change and you use an alternative recipe that we've also developed and print the exact same structure, what you end up getting is the purple curve. And so the deformation is changed by a factor of 2.5, even though it's the exact same material, exact same geometry. And so for this point, it's very important for these simulations to be accurate. It needs to sort of come with an integrated approach where it's considering both the hardware, the process, and the software at the same time. And that's where Velo's integrated solution enables accurate simulations, because we're providing all of those at the same time. And so can carefully calibrate the models to give the right predictions for the processes that are run on the machine. And finally, so in conclusion, the three areas I talked about today in terms of improving deformation correction and first print yield. First of all, on the Velo Sapphire system, we're using a non-contact recoater, which eliminates that major source of failure from many builds. The second thing is we have the ability to measure overlay and distortion before or after any build, or even during the build, to check to make sure that the lasers are well aligned in printing the correct shapes. And this allows us to quickly validate that the machine is healthy before running any prints and make sure that the parts come out geometrically accurate. And then finally, we have these thermoplastic deformation simulation capabilities built into our software, which allows you to do simulations of the part before you actually do the print, see how much the object is going to deform, make any adjustments that you want to, and then even apply pre-deformation to the object, such that when you actually print the object, you get the correct shape. Does anyone have any questions?